All right, this is actually section 8.3. 8.3 are polar coordinates of a complex number, and then DeMovire's theorem. It is a long section, so bear with me with this. Let me get this out of the way. So we're going to graph complex numbers. Hopefully you remember that too. There's a real axis and an imaginary axis. The real axis is your x-axis, imaginary axis is your y-axis. Same exact thing, you go over to your x left or right, then you go up or down. And that is in the complex number plane. So we have the complex number z1 right here. 3 negative minus 4i. So you go over to 3, down to negative 4, put a dot. That would be z1. Negative 2i plus 1. Well, you go over 1, even though the imaginary part's first. They're tricky here. Go down to negative 2i. This is z2. And you want to add z1 and z2 to get a new point. Well, you had to add the real parts together. 3 plus 1 is 4. Add imaginaries together. You get negative 6i. I'm going to have to move this down a little bit. Then we go over to 4, down to negative 6, put a dot, and that's z1 plus z2. Graph each set of the complex numbers. So we are graphing a plus bi from 2 to 3, which is, there's no I parts, which means they're vertical lines. And they do equal them, because it's got the equal to parts with our inequalities. 2 to 3, so anything, let's pretend that they're super straight. This is our graph right here. It gave us no I-coordinates, no imaginaries. Oh, I just started changing colors. So we have nothing to do with imaginaries, it's just vertical lines, since we're only using the x-axis. A modulus, or absolute value, right there, of a complex number is this formula right here. It will also be called the magnitude, which I don't know if this section uses that terminology. It does not. It just says modulus. It's also sometimes called the magnitude. You might want to write that down in case you come across that at some point in your mathematics career. So they want you to calculate the moduli of the complex numbers, negative 7 plus 24i and 40 plus 9i. It's two separate questions. We're just going to do it. There's two imaginary numbers here, so we're going to do it twice. For the first one, it's the square root, negative 7 squared plus 24 squared, which is 49 plus 576, which actually is a perfect, that can't be right. 20, let's check this. My paper sounds really incorrect. Oh, pen down. 49, what is this craziness? Delete, clear. 49, here we go, plus 576. 6, oh, so it's square root of 25, not 5. I have my paper, it says 5. I was a little off. So this is 25. For the second one, the modulus, magnitude, whatever you want to call it, 40 squared plus 9 squared. 1600 plus 81 gives us 1681, which is actually a perfect square of 41. On the back, graph the set of complex numbers z where the absolute value of z is less or is greater than or equal to 1, which is actually a circle at the 1s. So here's a dot, here's a dot, here's a dot. It's got the equal to part, so it's an actual circle. And since we're talking about greater than, oh, yeah. I think that's shaded wrong. I'm going to say that's shaded wrong. That wouldn't make sense. Look at my notes being wrong. Greater than 1 should be out here. outside the circle, not inside the circle. If it was less than or equal to 1, then it would be inside the circle, outside the circle. Eventually, we might talk about more about absolute value graphs and inequality graphs. I'm not really worried about if you can graph those or not. This is like the more important stuff. Going from polar form to complex form and doing DeMovire's theorem. That stuff's the more important stuff. So from here on out, for the rest of the notes, is the more important stuff. Things we need to know. Complex number, okay. Polar form or trig form is this function right here, okay. R is the stuff from before. It's the same exact R as before. And to get theta, to y over x, same exact thing as before. All right, so here, let's write out some things. A is -1. B is also -1 because there's a -1 in front of that I. So to get R, -1 squared plus -1 squared, and you get the square root of 2. To get theta, again, theta equals -1 over -1, which is 1, right? If you were to plot that complex number, you would end up in quad 3, which means we're not looking for 45, because that's when tan is 1, 45. We're looking for 225. Oh, equals tan theta equals 225. So our complex form is radical 2, parentheses, cosine 225 is 5 pi over 4 in radians. 5 pi over 4 plus I sine 5 pi over 4. That is our complex number in trig form. For part B, A is -4 radical 3. B is a -4. So we do our R. -4 radical 3 squared plus -4 squared. We end up getting 8 once you do all that fancy math work. You end up getting 8. Then we got to find theta. So tan theta is equal to -4 over -4 square root 3. We can punch this in the calculator if you'd like. It is a perfect second tan -4 divide parentheses -4 square root 3. Is that right? Parentheses. Oh, 30. But we are not in quad 1, we are in quad 3, which means that we are not looking for 30, we are looking for 210, which in radians is 7 pi over 6. So our trig form is z equals 8 parentheses cosine 7 pi over 6 plus I sine 7 pi over 6. Trig form and DeMovire is both of them are on the final exam. Next we go. So A for part C, A is equal to the square root 3. B is equal to -1. So we're going to put it, I'll change colors so you can tell the difference of the question, since we're getting a little jumbled. R is equal to the square root of square root 3 squared plus -1 squared. And that ends up equaling 2. Tan theta equals -1 over square root 3, which that is actually quad 4. And the reference angle is 30 again, because it's almost just like the previous example without the 4s. So we're looking at theta is actually 330. In radians is 11 pi over 6. So our trig form, z equals 2 parentheses cosine 11 pi over 6 plus I sine 11 pi over 6, closure parentheses. And lastly, D. I'm going to put D on a separate page. So here's D. We get 3I parentheses 1 plus I. I'm going to distribute that in. So 3I plus 3I squared. I squared is equal to negative 1. So this changes to negative 3 plus 3I. So A is negative 3. B is 3. So your R is equal to negative 3 squared plus 3 squared. That comes out to be 3 radical 2. Tan theta is equal to 3 over negative 3. If you were to actually graph that imaginary number, you would be in quad 2. Yes, you would be in quad 2. This is tan of negative 1, which is a reference angle of 45. But since we're in quad 2, we're looking for 135. 135 in radians is 3 pi over 4. So our trig form, 3 radical 3, oh, blah, 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 blah. 3 radical 2, parentheses, cosine 3 pi over 4 plus I sine 3 pi over 4, closure parentheses. And that's the last example. So going back, down here we have multiplication and division. There's no way around it, honestly. It's just using the formula. To multiply two trig numbers, you multiply r's, add thetas. To divide two trig forms, divide r's, subtract thetas. There's no way to remember it. It's literally like getting the formula down, putting the pieces in. You do have to make sure that your numbers are in trig form first, though. By chance that they may not be. So next page. Nope, I added a page. Okay. I just talked about that. So down here, multiplying, dividing complex numbers. Thankfully that these are already in trig form. So first part is multiplying. So z1 times z2. So I'm going to multiply 7 and 8 together. And then I have my cosine, and I'm going to add pi over 6 plus pi over 5. Pi over 6 plus pi over 5. Well, if you multiply 7 times 8, you get 58. You do not. That's just kidding. You get 56, not 58. Pi over 6 plus pi over 5 ends up coming out to be, once you get common denominators and add numerators, 11 pi over 30. And there we go, multiplied together. Next one, division. Z1 divided by Z2, 7 divided by 8, then cosine pi over 6 minus pi over 5, and we subtract our thetas. There's nothing to do with 7/8, so just leave it. 7/8. So we have cosine negative pi over 30 plus I sine negative pi, pi over 30. Okay, well, we're not done yet because we have negative angles. I don't want negative angles. So this is equal to 7/8. Cosine of a negative angle is the same thing that's positive version. So this is pi over 30 plus I, oh, no, it's not plus because sine of a negative angle is equal to negative sine of that angle. That's the true answer. 7/8 cosine pi over 30 minus I sine pi over 30. DeMovire's theorem. is when we're taking our trig form to powers. So there's these powers here. So you take your r to a power and you take your theta and times it by whatever power you're asking it to. But of course it also means that you need it in trig form first. So we need to get this in trig form first. A is a half, B is a half. So we need to find r. So 1/2 squared plus 1/2 squared, you do a bunch of fun fancy math, and you get radical 2 over 2. Then we got to find theta. So tan theta is equal to a half over a half, which is 1. So theta is 45, which is pi over 4 in radians, because we want to keep it in radians. All right, so our trig form is radical 2 over 2 cosine pi over 4 plus I sine pi over 4. Now they want it to the 12th power. Ooh, I need more room. So I want z to the 12th. If I'm taking z to the 12th, I take my r to the 12th. And I'm going to take my theta of pi over 4 and times it by 12. Radical 2 over 2 to the 12th becomes 1 over 64. And pi over 4 times 12 is just 3 pi. Now careful, when you're doing these questions, it may ask you to leave your answers in trig form, or it may ask you to change it back to imaginary numbers. If it does ask you to make it back to imaginary numbers, distribute 1 over 64 in, evaluate what cosine of 3 pi is with times 1 over 64 and change it back to an imaginary number. Make sure you are able to leave your answers in both forms. For part B, before we need r, A is 1. B is negative radical 3. So we need r. R is equal to 1 squared plus negative radical 3 squared, which is negative tan theta. Negative radical 3 over 1, which is just negative radical 3, which means we are in quad 2. In quad 2, we're looking at a reference angle of 60. So we're looking at 60, quad 2. 120, that seems weird. This can't be right. I'm so not in quad 2. This is quad 4. What am I talking about? Down, over. Yeah, we're in quad 4. We were looking at 60, that was a reference angle. We were looking at quad 4. So we're looking at 300, not whatever I was going to tell you. This is 5 pi over 3. Okay, let me change colors again so we can distinguish. So my trig form is 2 cosine 5 pi over 3 plus I sine 5 pi over 3. Okay, but we want to take this to the 5th power. So z to the 5th means 2 goes to the 5th, and our thetas get multiplied by 5. 2 to the 5th is 32, and then this becomes cosine 25 pi over 3. All right, onward we go. These are probably like really long notes. On the back of this page, we have the nth root of complex numbers. So instead of taking it to a power, we're actually finding the nth root and finding all the roots of something, which is this fancy formula. Now I'm going to do just one of these, because it is pretty time consuming. And I will pick, we could do the first one. It's pretty extensive. So we will choose the first one. All right, this is the formula right here that you need to know. Okay. There's an n, there's an r, there's a theta, there's a k, so there's lots of stuff to find out. All right, so if we're looking for the sixth root of z equals negative 729, that means a is negative 729, b is 0, because there is no imaginary part. So to get r, negative 729 squared plus 0 squared, well, that should be 729. To get theta, 0 over negative 729, which is just 0. Tan of 0 is at 180, which is pi. Okay, so we have r and theta. They want the sixth root, so n is 6. Write that down. N is 6. Are we good so far? In our trig form, I'll write that down too. Z equals 729 cosine pi plus I sine pi. Okay, that's the original trig form. But if I wanted to know what w of k is, so I want the sixth roots, so I want all 6 roots. So it's 729 to the 1/6. So I'm taking the 6th root of it. Cosine of pi, oh, there's a fraction here. Cosine of pi plus 2k pi all over 6 on top, plus I sine pi plus 2k pi all over 6. Now we are going to replace k with the numbers 0 to 5 and then evaluate. So if I put in 0, I gotta make these thinner. I don't want to do that. This is fine, I guess. Let me choose another color because I want this thinner. 729 to the 1/6 cosine, if I plug in 0 for k for the first one, that whole second part is 0. So this is just pi over 6. This ends up being, if you actually find cosine pi over 6 times it by 729 to the 1/6, you get 3 radical 3 over 2 plus 3/2 I. Next one. Now we're going to do, oh, of 1. There's a 1 there. So cosine, if we plug a 1 in for k now, we get pi plus 2 pi, which is 3 pi. 3 pi over 6 is pi over 2. I sine this ends up being 3i if you want to evaluate it. All right, now I'm doing w sub 2. 729 to the 1/6. So I plug in 2 for k. I get pi plus 4 pi, which is 5 pi. So this is 5 pi over 6. And you get negative 3 radical 3 over 2 plus 3/2 I. 3 more. Plug in 3. If I plug in 3 for k, I get pi plus 6 pi, which is 7 pi. So 7 pi over 6. This eventually evaluates to negative 3 radical 3 over 2 minus 3/2 I. If I do for 4, oh, if I plug in 4, I get 9 pi over 6, which is 3 pi over 2, once you reduce. This evaluates to negative 3i. One last one. If I plug in 5, I'll end up getting 11 pi over 6. And this evaluates to 3 radical 3 over 2 minus 3/2 I. If you notice that all the answers are actually some variation, because it literally just kind of goes around the unit circle. That's the only one I'm going to do. You should try the other two. Take them to class, do them there, ask questions, ask your peers, ask the teacher. They'll give you some insight. And that is section 8.3.